everyone is aware of the previous year assignments, huh? So can we please discuss about it if you want? Have you guys gone through the previous year assignments? Just checked. Asking.
Ma'am, where can we go to the previous year assignments?
Uh, okay, okay. There is one site, but I think that is not accessible to you. That's the problem. Okay, no issue. Actually, I couldn't. I am also new in this kind of live session. It's my first EADP, so I couldn't access that one. No problem. If you have any doubt, we can just discuss. So the main topic in this week is first the pure aluminum, the properties of the pure aluminum, like the density, the melting point. The melting point is very crucial. Always try to remember the melting point, which is 659 or 660 degrees centigrade. You'll be often asked about the aluminum melting point because it's pretty high, and also the boiling point, and the properties of aluminum, like it's paramagnetic, means it doesn't have any or doesn't show any magnetic characteristics. The main property is corrosion resistance. Like in iron, when we leave a iron rod or part on object in open environment, it will get rusted. We can see the rust, it's brownish color, but iron oxide. But in aluminium, there is one property like corrosion resistance. There will be one layer of alumina or Al2O3 formed over the particular part, which was under the normal condition or in the environment. But that layer is very thin. It's about 5 micrometer. You can't even see it in your naked eye, and it's white in color. That's why aluminum is always white, has a white surface and do not get corrode, which is a very prominent and important characteristics or properties of aluminum, using which a lot of industries and in lot of applications this aluminum alloys are used. Not only alloys, aluminum composites are used in aerospace engineering. There almost every type of parts from the aerospace or aircraft body or the aircraft components, like the optical components or mechanical components, all the components always have aluminum alloys. They are mostly wrought alloys because obviously after casting we need to give a particular shape and geometry to the object which will be made of aluminum alloy. So we generally use wrought alloys, but due to the characteristics of aluminum like ductility, low weight, uh, Young's modulus, no corrosion resistant, like high corrosion resistance, electrical properties, mechanical properties, these alloys are used. So next we learned about the purity, like aluminum has an FCC lattice structure with a lattice parameter of 4.05 angstrom. So because of that FCC structure, aluminum is brittle in ductile in nature, sorry, and that ductility increases with the purity. Obviously, purity means that aluminum is having uh, almost no impurities, and as aluminum is a FCC structure, so with purity the aluminum increases its ductility obviously, but also at the same time the strength decreases. The strength is quite low for some aluminum alloys which are like 1000 or 100 series, which are almost pure aluminums. Young's modulus and Poisson ratio, we got to know about that. For 1000 series, the last two digits uh, define or signify the percentage digits after decimal point. for aluminium, in case of the purity of the aluminium. Then we got to know about the impurities, sorry. So the impurities can come through many ways, like as we are extracting the aluminium from bauxite. So at the time of extraction, at different levels and different steps, the impurities can be added unintentionally, obviously. So impurities like iron, silicon, uh, phosphorus, magnesium, nickel, manganese, vanadium, calcium, titanium, etc., etc., etc. can be added. So there are types of or stages where these impurities can be added, like from refractory lining, from the crucible where the aluminium is melted, from the tools that are being used for aluminium extraction. From these arrangements, the impurities generally come. Then after impurities, there are some inclusions. So it's also nothing but impurities. So inside that aluminium alloy, some oxide, nitride, some compounds also can be present. Those are called inclusions. Sometimes these impurities and inclusions are also necessary. Like impurities include silicon, and there are silicon, aluminum silicon alloys. So it's not like we always have to cancel out the impurities. Sometimes, if the impurity is at with a certain amount which is needed, which will enhance some properties in the aluminum which is needed for a particular application, we generally don't just cancel out the impurities. We let the impurity be present inside the alloys. Effect of impurities, so there are different effect for each impurities. Like for iron and silicon, intermetallic compounds may form, and these intermetallic compounds also are brittle in nature often, that can enhance the brittlity, that can uh, modify the failure mode or mode of failure of a particular alloy, of a particular aluminium. There are impurities like titanium, chromium, manganese, vanadium, which increases the resistivity, which affect the electrical property. But sometimes if we are making some components that needs a lot of resistivity, that we don't want the current to pass from that particular electrical component, so we can use aluminum alloy there, which will have this impurities. So after that, some application was taught. Then the extraction process. So in extraction process, we got to know that alumina is a stable oxide. So and also it needs more than or almost 2000 degrees centigrade to be processed using carbothermic reaction, by which the aluminium can be extracted for alumina. But it's not viable, it's not feasible, because there will be some problem, like refractory will be needed for such high temperature to sustain that temperature. Some unwanted formation of alumina carbide may take place due to that refractory or refractory lining. So these are some problems. So that's why we generally go for the electrolytic uh, decomposition of alumina by Hall-Héroult process. So first we extract the alumina. We try to get pure alumina from the bauxite ore, using the Bayer's law or Bayer's process. After that, when the alumina is with us, we go for the Hall-Héroult process, by which we extract the aluminium from ale tool. There also some points are there. So then there is the mechanism of decomposition. So Hall-Héroult process is nothing but the electrolysis of alumina with a certain arrangement of cathode, anode. Yeah. uh, yeah, 1 minute. So after that, we go for when the alumina is melted and that is present inside the crucible. So the aluminum is extracted using decomposition. There are few formulas. I think you don't need to remember the formulas, but just go through them so that you can understand what is happening there. And after that, the alloys at designation that we have already discussed. So yeah, Vanshika.
Yes, ma'am. Actually, this is a best process, the doubt. The cool liquor that we get after the heat exchanges, basically, we are adding ALOH thrice to this for thickening. Am I right? Uh,
You are talking about the heat exchange
After the heat
after heat
exchange,
exchanger. Yeah,
yeah.
yeah. Please tell.
So we're adding ALOH thrice into it so that it precipitates out. Like ALOH thrice precipitates out, or Al2O3 precipitates
Yeah,
out.
yeah. Yes.
Uh, I, yes, ma'am.
So you want me to discuss the equation or the
No, actually, my doubt is that what are we getting after addition of ALOH thrice as like that acts as a nuclei for precipitation of what exactly? I didn't get it.
so yeah, AlOH3 is with the fine particles are added, then it's subjected to cooling, and then it's subjected to calcination in a rotary device. So because of that rotation, its motion, and the adding of AlOH3, some reactions take place and anhydrous alumina or Al2O3 is achieved where the what say H2O is also eliminated. So that's what we were aiming for, na, that anhydrous alumina, so that we can further go for the Hall Héroult process, which is a pure alumina we are getting.
Yes, ma'am. Ma'am, all these processes are taking place together in the rotary kiln, or how is it happening? Or we do it
This
step by step.
step this step is taking place in the rotary kiln. This step particularly, where AlOH3 fine particles are added, and this Al2O3 precipitates are subjected to cooling. So this process is taking place there so that we can get that precipitate of anhydrous alumina.
After this, it is. I mean, I didn't understand. Like after this, then why it is subjected to calcination?
It's like when alumina is achieved to get anhydrous alumina, because after mixing the AlOH3, when the precipitate is achieved, that will be hydrated, means the H2O will be present inside that alumina which is precipitated. But to eliminate the hydrous portion or the H2O portion, we are going for the calcination in the rotary bar or rotary chamber.
Okay, okay, ma'am, I got it. Thank you.
Yeah. So you need to just search for the equation or the reaction. Then you'll understand the calcination is just eliminating the hydrous portion. Because from beginning we are starting with bauxite, which is nothing but a war of two different compounds, gibbsite and diaspore. The all two compounds are having a hydrous portion inside it. So at the last stage, we after processing the all the things just to get extracted the alumina, we are at the last step we are eliminating the hydrous portion.
Yeah, ma'am, I got it.
Anything else? So Before alloy designation, there are the topics in which the Sievert's law I'll get back to you in the next class in a more detailed way. And apart from that, there are fluxing. The flux agents are mixed to remove the oxide inclusions. So this all processes are basically the gas extraction or eliminating the gases which are present as an impurity inside the alloys, aluminum alloys. So this fluxing, then vacuum, uh, which is using the Sievert's law, then gas purging. All the processes are used to eliminate the gases. But at the last stage, filtration is taking place. We are doing filtration basically to remove the solid inclusions or impurities. And then in lecture 4, we got to know about the designations. So as I said about the wrought and cast alloys, their alloying elements, different alloying elements which are giving different properties. Uh, yeah. One we can do one thing in next class. We will be seeing a few example of wrought alloys of same grades and different grades, and we'll be seeing the properties so that we can understand how the properties are varying with different impurities, because here it's only said that yeah, using or mixing more amount of silicon, we are getting 4000 series alloys, or mixing magnesium and silicon, we are getting 6000 series alloy. But what at what percentage they are mixed, or exactly what properties they are enhancing, why we are mixing this impurities or alloying elements, and what are the different grades of a particular designated wrought alloy or cast alloy, we'll be seeing, so that these things will be clear to all of you. Apart from that, yeah, that um, phase diagram of aluminum silicon, the hypereutectic and hypoeutectic, the problems regarding the hypereutectic, and that's it. Up to the silicon growth only. So up to this, if you have any further doubt, we can discuss. No doubt. If you have any doubt according to the current semester assignment, we can also discuss. If you have already, could you have more practice question on photographic diagram? Okay, right now I don't have any practice question on the phase diagram or any topic, but yeah, I can collect question from next class. Okay, microstructure. Right now I don't have any diagram, but microstructure, no, वो तो नहीं है अभी मेरे पास कुछ. You can find in online also different paper. You can search some papers also if you are interested to see the microstructures of different aluminum alloys. It will just show different types of microstructure due to the different alloying elements. But microstructure morely depends upon the process that you are using your how you are cooling down after melting, if it's being quenched or if you have gone through some heat treatment. According to that you can change your microstructure. And also again, based on the application, you can go for different microstructures, because ultimately all the properties are defined by the microstructure, is the most important things. ठीक है, मैं नेक्स्ट क्लास में माइक्रोस्ट्रक्चर ट्राई करती हूँ अगर दिखा पाती हूँ इसलिए. Any more questions or doubts or anything else you want me to discuss from the week 1 lectures? So you want me to discuss about practice question on eutectic diagrams only, or on all the topics? Some possible questions. So you guys are from MTech or PhD or BTech? What? One by one you can tell me. You can also introduce yourself. Yeah, Sridhar.
Yeah, ma'am, it's better if you call out the names. Anyway, I'll start myself.
Okay.
I am a BTech in Mechanical Engineering graduate. I passed out in 2006.
Okay.
So after that, after various industries, working in welding industry.
Okay.
So recently, I could see the change. Take it our greatest example of Vande Bharat Express, where before from now stainless steel to they're shifting to aluminium.
Yeah.
So the recent trends in aluminium, to understand those things, I opted for this course to learn more about aluminium.
Okay. Apart from this industries also, the I can talk about the aerospace industry, where you could see NASA, ISRO, all the organizations are using aluminum alloys. They are trying to build different aluminum metal matrix composites using different alloying elements to achieve or to make different mechanical and optical elements components. And
Great,
there are a
great.
lot of research is going on this type of aluminum metal matrix composite and metals to enhance the properties, more feasibility, because aluminum is cheaper. Aluminum has its own properties, and the main factor that I believe is aluminum, although it has a lot of properties, the main thing is aluminum is a FCC crystal. Because we know for BCC crystals there is something called ductile to brittle transition temperature, which will be not applicable for FCC structures. This is the most advantageous thing about aluminium, because for that you can use aluminum alloys or metal matrix composites in any industry or for any application. Like for aerospace application, the aerospace components needs to sustain very high temperature difference, very high environmental gaps, like the environment or the humidity, temperature, pressure, everything is so different in space, and they need to sustain that environment there for longer time period. So aluminum can do that work where BCC crystals cannot serve the purpose. So anyway, some advantages. Okay. Thanks, Kiran. And I'm also from mechanical background. So I am a direct PhD at IIT Delhi. So after BTech, I joined IIT Delhi. I'm doing PhD in mechanical engineering as well. So no issue. Next,
Okay. Yeah, because my metallurgical background is little less. That's all.
okay,
But after coming to welding, now I'm into metallurgy also. Even though my basic qualification is mechanical,
okay.
now slowly dealing metallurgical things also.
And
That's all.
mechanical people also need to understand the metallurgical aspects as well, because after everything is done, we have to opt for different materials for our different applications. Even if we are just making some new designs and things, we need to uh, give different materials to our design, because our all the designs of mechanical engineer is based on the material that we are choosing. So we have to have knowledge about material science and metallurgy in today's world.
Yes.
So it's fine.
Yes, yes, sure. That's why even after passing out in 2006, I am spending time to learn at this age the basics of metallurgy in aluminum also. Because I had experience dealing with the steels. Now even aluminum is new, so that's why I opted for this course.
Okay.
Because so far I
So
don't
I'll
have any industrial experience.
I'll
So
discuss
direct.
about the different grades of aluminium with their varying properties, with varying percentage of alloying element in the next class, so that all can understand how these alloying elements are playing the important role in the alloy designation or alloy properties for different applications. Anyway, thanks, Kiran.
Okay.
Vanshika, so your background?
So first of all, hello everyone. Actually, I'm a BTech third year student
Okay.
at NIT Calicut. I had a lot of interest in metal matrix composites, and like I had an internship last semester, so I got to learn about magnesia matrix composites and things. So it was really and its structural applications basically. So it was very intriguing to me. So I decided to take on the selective to learn more this sem.
Next, anyone? Nishnath, Nishant, sorry.
Hello.
Yeah.
Yeah. Hi everyone. My name is Nishant. I have done my diploma in metallurgy 2005, and after that I had 13 plus years of experience in India as well as abroad. So working on different organization, uh, basically dealing with quality control of dealing with various materials. So, as you said, majority of the materials we're dealing is steel materials. So, apart from that, aluminum was also an important alloy. So, in order to go in depth of this material, I thought of came for this course.
Thanks.
Yeah, thank you.
Siddharthan, then Pranav, Joseph.
So I'm Pranav. I am currently doing my MTech in automotive engineering in Amrita Vishwavidyapeetham. So I did my BTech in mechanical from Amrita itself.
Okay.
So as a part of my third semester elective, we were asked to do a move on course where we are supposed to choose a course from NPTEL or Coursera. So I found this course was close to automotive because
Yeah.
many of the castings and many components are made out of aluminum and it's alloyed because of its weight and other properties. So that is why I've taken this course and increase the knowledge also in automotive related to aluminum.
Okay. You are not audible. Or Joseph.
Again, I'm doing PhD in Karunia University, Coimbatore. My research topic is aluminum composite. So I'm interested in giving this class. Thank you.
So you are going to make aluminum composite?
Yes, of course.
Okay. So you'll be using some conventional ways to make aluminum composites, right?
Aluminum composite by strip casting, we have decided. Depends. We can change. Strip casting is the
Yeah, yeah.
process. Yeah, thank you.
Yeah, in steer casting also, when
Yeah.
people make aluminum silicon alloys or
Okay.
magnesium alloys, the 6000, they mix
Okay.
silicon and barium and sodium, any one of the elements.
Madam, how about aluminum 7000 series?
7000 series. Yeah, 7000 series is
Yeah.
also used for, based on my knowledge, a lot of advanced components are again made of 7000 like 7225,
Okay.
7270.
Okay.
It's again, it is having many properties. Uh, yeah,
Okay.
like high Young's modulus, high ductility,
Okay.
low strength. Also, I think
Okay.
sometimes it is also heat treatable. People often go for the precipitation hardening and other type of heat treatment as silicon alloys.
Okay.
It's
Okay.
also very beneficial.
Thank you.
There are
Good
also
evening, madam.
processes like plasma arc sintering and other pressure sintering processes which are used for making aluminum composites.
Thank you. Okay.
So, okay, if you have any other doubt, we can discuss.
Hello.
Or yeah, yeah, yeah.
Uh, Madam, I am R. Siddharthan.
Okay,
I am doing my part-time research work in Anna University, Chennai
okay,
on metal additive manufacturing, especially on aluminum alloy.
okay,
So I have joined this course for getting more knowledge about the aluminum alloy, madam.
okay.
I am in the stage to find out the research gap. So I think this course will be helpful to know about the aluminum alloys. That's why I have joined this course, madam.
Yeah. So, which process you will be using for metal additive manufacturing?
Metal additive, CM, cold metal transfer.
Okay,
CM,
CMP.
cold metal transfer, machining process I am using, madam.
Okay. I'm also working in additive manufacturing, so that's why I asked.
Uh, okay, madam. Okay.
So, we can just start as time is left. So, we can just pick up any one topic and discuss about it. I can pick up any one topic from this 5 lectures, or you guys can also pick me up any topic from the last 5 lectures. Anyone? So, should I ask you some questions from the last 5 weeks? And you can just turn on the mic and answer. Is it fine? You can just raise your hand by saying yes. Yeah, okay. So we can do that also. Fine. Yeah, okay. Uh, already discussed about the 5 lectures, but again, just for the purpose of question answering, I'm asking again the same questions. So if I say or ask that why this aluminium is having such property of corrosion resistance, or is it any rust kind of thing that will be there in aluminium, or what is there which resists the oxidation of aluminium, or what? Anyone? Yeah, please.
Al2O3 formed.
Yeah. So A2O3 is a white surface, a thin layer of 5 micrometer which resists the oxidation. Right. Okay. So if I ask you that if I increase the purity of the aluminum alloys, what will happen to the strength and the ductility?
The strength decreases and the ductility increases with increase in purity.
So why the ductility increases with the increasing of purity of aluminum in aluminum alloys? What is the lattice structure type of aluminum?
Um, I got this like from the lecture from this class today that it's because of the FCC structure of it that the ductility increases, but I don't know exactly how that happens. Could you elaborate on that?
Okay, actually, what happens is if you see FCC structures, it's face centered cubic structure. So, what happens is if there is a cube, there will be 8 corners. So, 8 atoms will be present in all 8 corners, and along with that, in all 6 faces, there will be an atom. So this is the arrangement. But if I'm comparing this FCC structure with a BCC structure, in BCC there is atoms in 8 corners and there is one atom at the middle. So because of the arrangement only, there is no space available in BCC, means it's said that BCC structure is a compact design. It's a very close compact design rather than FCC. And there is one concept of slip. So slip is nothing but uh, just moving one plane with respect to the another plane, like how dislocation moves. So with or through the slip plane, when the dislocation starts moving or according to the slip planes, it will start moving, or it according to the active slip planes or through the active slip planes, the dislocations start moving. So for FCC, there are few number of slip planes. I don't remember the exact number, but I think there is 5 active slip planes among 12 slip planes. But in case of BCC, there are lot of slip planes, but the or slip system rather, and the number of active slip system is lesser. But there are lot of slip system present. So slip system is nothing but um a slip plane and a slip direction. So a plane in which the dislocation will move, and a direction in which that dislocation along that slip plane will move. So this slip plane and direction makes a slip system. So in case of FCC, the number of slip system is lesser, but in BCC number of slip system is more. But BCC is a closed pack structure. So in FCC, this sleep or dislocations can move, but in BCC, these dislocations cannot move like they can move in FCC. And because of that, the FCC, the strength of the FCC is not that much because the slip dislocations can move, the crack or not crack, but this dislocation hampers the strength. But in case of BCC, because of this close pack structure, BCC makes a material or element or object brittle. and at lower temperatures, these brittle or BCC structures gain more brittlity and it can be fractured. So if you guys know about Titanic, so how Titanic, what happened to Titanic is uh, when it uh, means when it was inside the water, there was a huge chunk of ice bar. So when it collide with that huge chunk of ice bar, due to the lower temperature of the ice bar, the Titanic was made of iron and some alloy of iron. And due to that BCC structure, it collapsed, and that happened because BCC structure shows more brittlity at lower temperature, whereas FCC structure doesn't change their properties at even lower temperature. So this is called ductile to brittle transition. It's nothing but some materials which are ductile, they will show brittle nature or property at lower temperatures. PCC structures show more brittle nature or properties at lower temperature, but FCC doesn't show that. That's why I told that aluminium has a great advantage of having this FCC structure, because FCC structure will not show any ductile to brittle transition. And if someone is working with a material which shows BCC crystal, which has BCC crystal, they always worry about the temperature, because at lower temperature they may collapse. And due to that FCC structure, as there is space for the dislocation to move and this sort of properties, the ductility increases. If there is any crack and we are applying the load, the crack may undergo some deformation, and or the object may go undergo some deformation and the crack will grow inside that object, and that can means collapsed, or that can break. But for FCC, for this type of aluminum alloys, as the ductility is more, we know that what ductility means when we'll means apply some tensile force or so, it will try to, after removal of the force, it will try to be at its original shape and size. And ductility will not means ductile materials do not get cracked or broken very easily. This is an advantage of the ductility over brittlity, but obviously again, according to the application, we always go for the materials and its properties. It's not like we always go for the ductile materials. We uh, will opt for the properties according to the application. So yeah, we have some raised hands. Nishant.
No, you asked for raising hands before.
Sorry, can you please repeat? I couldn't hear. Vanshika, yeah.
Ma'am, actually, it's in continuation with this only. Like I've got this doubt because basically adding any alloying element to a parent lattice is like adding an impurity to it, if I'm not wrong. So, and I've heard that like if you add an impurity, it's like adding an alloying element can help, make the flow of the dislocations allowing elements can make the flow of the dislocations little difficult, so that can increase the strength.
Yeah.
So actually increasing the impurity and like decreasing the purity of aluminium can actually increase the strength, right?
Yes.
But we study it as different.
What? Which point is different?
Like we study that as the purity decreases, the strength also decreases. Am I right? Like, or is it the other
No,
way?
no. If the purity increases, the strength decreases. It's reverse relation.
Uh, okay, so like I'm increasing the purity and the strength is going down.
Yes.
But yeah, ma'am, like adding an alloying element can increase the strength of the material, right? Like
Yes.
that material. So if you consider an alloying element like an impurity, then I don't know how that's
Means
related.
purity means if we are having aluminum alloy, if that alloy is having 99.999% aluminum, means it's the most pure aluminum. It doesn't have much more, means a lot of impurities. But if we are increasing the impurities, means we are decreasing the purity. So by adding more and more impurities, means alloying elements, we are increasing the strength. So when we are adding the impurities or the alloying elements, we are decreasing the purity, and this is how we are increasing the strength by adding the alloying element. So what is your doubt? Yeah, please, Vanshika.
Uh, okay, ma'am, I was just taking a bit time to process that. Like, okay, I'll just go through this again. I think I was bit confused with it. I'll just go through this again.
Yeah, see, just as a recap, so if we are having an aluminum alloy which is having 99.999% aluminum, so that means it is having 0.001% impurity. So this impurity can be, for example, silicon. So we are having an aluminum alloy which is having very less percentage of silicon. So the impurity is very less. So we can consider this aluminum alloy as a ultra uh, something pure, ultra pure aluminum alloy. But if and this aluminum alloy is having very high ductility because the aluminum percentage is high. But if we are adding more silicon, so silicon will introduce some brittlity because the silicon structure itself has a mesh like structure, and all of because of these properties, it will introduce some brittlity. So we are adding more silicon. Maybe we have introduced 1% silicon in that particular alloy. So right now we have 99% aluminum and 1% silicon aluminum alloy. So we have decreased the purity. Purity means aluminum percentage. In this particular aluminum alloy, I have decreased the aluminum purity and I have increased the impurity as an aluminum as an alloying element, silicon. And this is how we have introduced some brittlity, and this is how we have increased the strength. So, as a recap, so we have decreased the purity, means we have decreased the aluminum percentage, but we have increased the strength. So, this is what is basically done by doing the alloying.
Oh, okay. Yeah, now I get it. It's basically when you say purity of aluminium, you mean like how pure the
Aluminium
aluminium
percentage.
itself is. And when you're saying it in an alloy situation, then you're talking about how much aluminium is present
Yes.
in it.
In
Okay, okay.
all cases, purity means how much aluminum is present.
I
There
get it
is
now.
one topic that was discussed was something like aluminium, pure aluminium, and then ultra something super pure aluminium, then extreme pure aluminium, then ultra pure aluminium. It was saying
Yeah.
99.8 and to 99.949% aluminium, then it will be called highly pure aluminium. When the aluminum percentage goes beyond 99.999%, it's called ultra pure aluminum. So purity means only aluminum is present.
Yes, ma'am. It's clear now.
Okay, so there was another raised hand, I guess. remember who was it. It was
What is the application of ultra high purity aluminum? Where do we use these ultra purity aluminum?
I'm not very sure about this answer, but I don't think this ultra pure aluminum has a very basic kind of application like in industries, but it will certainly have some applications because if people are talking about ultra pure aluminum, if they are trying to extract ultra pure aluminum, then there must be some application. It can happen. I'm not very sure about this answer, but I'm just thinking about it. Like, it can happen that I want to eliminate all the impurities that are generally present inside aluminum, like the impurities we have talked about: vanadium, magnesium, manganese, silicon, iron, copper, and I want to add some other alloying element and want to make some new element, new metal alloy. In that case, maybe I want ultra pure aluminum so that I can add some element of my choice to make a new material. It can happen, but I'm not sure about this answer, sorry. Any other question, or I should continue with the question answer session? Fine. So if I ask, uh, what is the process of cancelling out a solid inclusion from aluminum alloy? What is the process called?
Filtration can be done.
Yeah. Okay. Next is, if there is a fill in the blanks, like using dash process, uh, NaCl KCl is used to remove oxide inclusion.
Fluxing.
Yeah, correct. Next is the very common question we have already discussed. What is Sievert's law? The expression.
That's AB equal to root over K into PG, which is PG is the partial pressure of the gas present, and like CD is the concentration of the gas that is dissolved in the.
Yeah.
What is the value of equilibrium constant of that? Okay, that value, K value.
It will be calculated from the partial pressure and the concentration of the particular gas which is being dissolved. According to using that, we just eliminate the gas. It's dependent upon the gas which is being dissolved.
Okay.
It will be different for everyone.
Yeah, yeah. I got it. Thanks.
I need to check this equilibrium constant again. I'll just tell you in the next session with some definite values. What are the values for different gases? Uh, why or what do you feel if we want to extract aluminium from alumina using carbothermic reaction? What will be your comment? What happens? No one?
I guess alumina is like a very stable oxide, and using carbon to reduce it is not possible because the Ellingham diagram or very high temperature will be needed for it. So it's not feasible.
Yes. How much is the temperature for aluminium?
2000 degree.
What are the typical application of pure aluminium? Name some applications you feel where pure aluminium is used.
Engine blocks.
Okay. Then engine blocks. I
I
think
guess like in the bonnet of the engine.
okay.
Yeah, also car or the car wheel plate can be made with it.
These are aluminum alloys.
Ah,
They
okay.
have a
The plate.
certain strength.
Oh,
Electrical wire.
Okay. Anything else? In packaging, food packaging, we often see the aluminum foils to wrap our food.
ma'am, is that like pure aluminium?
Yeah.
Okay.
Pure means it's not ultra or super pure or even highly pure. It's
Like
alloy,
CP.
but it will be somewhat like 1000 CBY.
Okay.
Um,
Chemical industries and architecture.
Another thing, what I feel is there is another characteristics of aluminium, which is like aluminium is highly reflective material. It's a white metal, like aluminium, copper. These are highly reflective material. So, because of the alloying elements, the reflectivity, refractivity, these things also changes. So, what I feel is, as you asked me, the application of ultra pure. So, I think the reflectivity of ultra pure aluminum will be the highest. So, according to that, we can think of the application where that high reflectivity is needed. We want to reflect back all the lights which is coming towards a particular component. There, that ultra pure aluminum can be used. That ultra pure aluminum will be having the most ductility we can ever think of. So that ductility property where it will be used, but the reflectivity I really feel it can be one application. Okay, so let's move on to the next question. Okay, uh, what will happen if uh, any aluminum silicon alloy is under cold or hot rolling process? What will happen? The silicon, there is there any working of the silicon particularly in that alloy, in that aluminum alloy, if it's undergone of some hot rolling process?
Yeah, it will cracking may happen.
Yeah, excessive edge cracking happens due to the silicon. It's again due to that brittle nature of silicon, its mesh like structure, and its extendable property bonds, and its tetrahedral shape.
What is the crystal structure of the silica?
It's like a tetrahedron.
Tetrahedron.
जैसे मैंने दिखाया ना अभी टेट्राहेड्रन जैसे कार्बन होता है ना
Yes, yes, yes.
like the carbon tetrahedral shape. It's the same block, same row element as the silica, but it has same structure. Next, we can go for a question like, yeah, as she said me, she asked why we are subjected to calcination in the rotary kilns, uh, even after getting the alumina precipitate. Answer? Anyone else? No one?
What is the question?
So it's like after having the precipitate of alumina or pure precipitate of alumina, we are still going for the next step like calcination in a rotary chamber. So why we are going for that?
To remove the hydrous part.
So that we can get the anhydrous alumina.
To generate anhydrous
Yeah,
alumina.
yeah, fine, fine. Uh, what is anode effect? No one? Try something.
It's an electrode.
Yeah, anode is electrode. Then what happens in anode? Or what is anode effect? What happens? Any idea?
I guess like it's the formation of a thin film around the anode because of little amount of CO2 which has been formed, like being present in the bath, and yeah, it prevents the normal working of the anode. But like, could you tell me what exactly is that film made of?
It is like around the there is a coated alumina, right? In which this decomposition reaction will take place, right? So in that chamber there is a cathode, there is an anode, there is a refractory lining in the cathode. So when the alumina percentage goes down below 2%, there will be an interruption in the process. The normal operation will be interrupted because there will be a gas film between the anode and the bath, because as the electrical contact between these electrodes will be disrupted as the alumina percentage goes below 2%. So this is basically anode effect.
Mom, like it's due to the formation of a film on the anode. Like, what I didn't get the
It's like
exact.
when the alumina needs to be present inside the whole chamber, right? In which the decomposition is taking place and we are getting the aluminum, right? So if the alumina percentage is somehow going down below 2%, it means very less amount of alumina is there. Then there will be interruption between the contact or electrical contact between the anode and the bath. The bath needs to be filled with this alumina na. तो alumina कम हो गया तो there will be gas film which will adversely affect the normal operation. The gas film will be introduced, means the alumina due to the alumina shortage, the gas film will be introduced between this anode and the bath where the alumina was supposed to be present. So because of that,
Yes,
uh,
ma'am. Ma'am, actually, does this have anything to do with the sodium being dissociated by the cryolite or something?
by the cryolite. Okay, alumina is fed into the molten cryolite bath. So where the electric current is passed at certain temperature like 990 degrees centigrade. So at 990 degrees centigrade in the cryolite bath, the molten alumina is made, means alumina is melted. So in that, when the alumina goes down below 2%, this happens. मतलब ज़्यादा वो कम हो गया by chance in between the process. We need to supply the alumina continuously uh, so that there will be no interruption between this electrical contacts between these different electrodes and the bath in which this anode and cathode or refractory lining is present.
Yeah, ma'am, I got it.
Okay, so when when there will be sodium vapor started means if you see any sodium vapor at the time of decomposition, what will be indicated by this? What this type of sodium ion vapor indicates? Anyone? So what are the reactions? याद करने की जरूरत नहीं है, बस kind of.
Does it have like if the sodium vapor production has started, that means that Al2O3 will reduce in the bath, and the normal functioning will again be hampered because of the film formation. Is it?
It's like the decomposition is started. So as soon as this sodium ion and other ions or sodium vapor will be started producing, then it means that the uh, reaction is taking place in which the aluminum extraction will be done, like the decomposition is taking place.
Okay, ma'am. Yeah.
When the alumina is added in the cryolite bath, if we are seeing some sodium and fluorine vapors coming out of that region, that means the decomposition mechanism or decomposition reaction is start. Okay. So there are two theories in which we can get how the aluminium is production is going on, right? So I'm not going to that particular equations. I don't feel you need to remember these equations, but if you need for the exam purpose, you can remember. So it's like for fluorine that what you are saying for sodium is like if the formation of fluorine is enhancing with time, is being increased, that means that alumina shortage is taking place, not for sodium.
Okay, mom, understood.
Okay. Baki, the rest we have already discussed about the designations. So, uh, so we can recap about the designation. So 1000 series is the purest alloy of aluminium, which will have 99% and more than 99% aluminium. 2000 will have copper alloying element, 3000 will have manganese, 4000 will have silicon, 5000 will have magnesium, 6000 will have magnesium and silicon, and 7000 will have zinc, some magnesium, 8000 will have lithium, and 9000 is not really used. And it doesn't mean again that these some thousand alloys are only having this alloying elements. All type of alloying elements will be present in all designated alloys, but it's all about what is the major alloying element that we are considering here. Similarly, there are a designation for cast alloys, like for 100 series, it's the purest. More than 99% aluminum will be present in the 100 series. For 200, it will be copper alloying element. For 300, it's a silicon magnesium and some copper. For 400 series, it's silicon. For 500 series, it's magnesium. For 700, it's zinc. And for 800, it's strontium. Sorry, it's tin. So these are the 8 or 7 alloy designations. And also for 100 series, if there is dot and then 1 or dot 0, that signifies dot 0 signifies as near net shape, and dot 1 signifies as ingot, which has to be further processed to give a particular shape according to the application. So this is all about today's live session, I think. The rest, the fluidity, hypoelectric, hyper, we have already discussed a lot of time. So if you have any further doubt, you can ask, or else we can end this session. We'll meet in the next session. I will try to come up with the solution of the questions that was raised today, but was not cleared very nicely today. And yeah, we'll discuss about the next week 2 lectures. So is it okay?
Thank you, ma'am. Yes.
Yes, thank you. Thank you for joining. You guys have really gone through all the lectures. That's why you had the doubts. It's nice. So we'll meet in the next lecture, which will be on next Tuesday from 6 p.m. to 8 p.m. So, okay. So bye. Take care. Good night.